Today I'll be going over tail recursion and why it's important to use whenever possible when you care about optimizing for space or time. Tail recursion is an extremely important concept in functional programming. I'll be using OCaml today. It's a functional programming language with both functional and imperative constructs. If you don't know what those are, that's totally fine. Just stay tuned and enjoy the video. Alright, so the example that we'll be going over today in this tutorial is the factorial function. The factorial function is a very simple mathematical function multiplying a single number by the number below it, by the number below that one, all the way and on until you get to 1. So let me demonstrate what I mean by that. Say you want to calculate the factorial of 5. Okay? So in math it's going to look something like this. It's denoted by this exclamation point symbol here. That is actually going to equal 5 times 4 times 3 times 2 times 1, which is equal to 120. And this is the same for any number. So if I had something like 3 factorial, that's just 3 times 2 times 1, which is equal to 6. In OCaml, this is going to look something like this. I'll explain this syntax for any of you who are not familiar with OCaml. Let is a keyword that lets you create functions. So in this case, we're creating a function called fact. With this rec keyword, which stands for recursion or recursive, which basically allows us to call the name of the function fact within the body of the function itself. So you can see that this is indeed a recursive function, where fact is calling fact itself on some different parameters. So this is why we need the rec keyword here. Fact is just the name of the function as we described. N is going to be the input to the function. So we saw in our original example 5 factorial. So in this case we put 5 here in our fact. So fact 5, that would give us 120. And we can test that out by actually doing it right now. So if I did fact 5, we'll see that we indeed do get 120. Okay, let's go into the if statement. If n is less than or equal to 1, then we return 1. Otherwise, we return n times fact of n minus 1, so the number below it. And this is exactly how the factorial function is defined. This looks all good, and we can try some other numbers here to see that indeed this works. Great. Now here's the problem. The problem arises when we think about what exactly OCaml has to do to compute these factorial values. So this is what happens when you unpack fact 5 the way OCaml would handle it by the compiler. So you can see here that we have a triangle-shaped pattern where the compiler would have to go through every single value within the call stack. So starting from factorial 5, goes to fact 4, fact 3, fact 2, fact 1, all the way until it has no more recursive calls to process. Then, once we get to this step, we're able to start evaluating the sub-expressions one by one, starting from the most inner parentheses here, then going outward all the way until it hits 120. And this might not seem like a big deal, but imagine you had to calculate a number like factorial of 10,000. That's going to take a ton of space when it comes to actually writing this out. Of course, the computer doesn't have to write this out, but it does have to keep all of these numbers in some sort of memory. And that's where it gets a little bit tricky. With a function like the factorial function that we described here, it's going to get really messy real quick because it has to keep storing the value of n being multiplied to the next recursive function all the way until it hits to the bottom, which is 1. Then it has to start doing it one by one by one by one, and that's just going to be very inefficient for the computer. So that's where tail recursion actually comes in and saves the day. So we have a new function. We call it fact_tr, tr standing for tail recursive, of course. And here's our new definition. So it's mostly the same, except you'll see a few key differences here. First of all, not only does it have just the one input n, it also has this input called acc, or accumulator for short. So the key difference here is that we actually have both the if statement and the else statement with the same sort of logic, except instead of returning 1 when it hits to the base case, it is actually going to return ACK, which is the input to the function itself. And you'll see why that's important in a second. The other thing to note in mind is that in this else branch here, there's no n being multiplied to the front of this function anymore. In fact, we only have factr with two inputs. The first input with n minus 1 being the same as before here, as you can see. But the second input, where the ACK is stored, we're actually multiplying n directly to the accumulator itself within the input to the next recursive call. So if we do that here, and we actually test this out on 5 and 1, the reason why we use 1 in this case for the accumulator is very simple. It's whatever the base case of the original function is going to be. So in our case, because we know the factorial function always has to cap down to 1, and we're multiplying whatever it is to 1, and then so on and so forth, we're actually going to use the accumulator of 1. That indeed we get the same answer, 120. So the key difference here is that in the original function, our factorial function had to multiply n to the outside of the recursive call. And remember, that's what gave us this triangular structure where we had to multiply 5 and then multiply it to the unresolved recursive call of factorial 4, then 4 times factorial of 3, and then factorial of 3 till we got to the base case of 1. So it had to continuously store 5 times 4 times 3 times 2 and so on and so forth without actually being able to evaluate any of them because we didn't know what was going to be the next lower factorial value. In this case, however, I've unpacked the definition of factr as the OCaml interpreter would unpack it, just like we did before with the original function. But now the key difference here is instead of having a recursive call every single line with a series of things multiplied in front of it every single time because of our call stack, notice how we only have 2 different numbers in each of the lines, and that's both the inputs of factr. This is really important, and notice how this works is it always decrements the first input, which is n, as desired, but the second input, which is the accumulator, it's going to be going up every single time by updating the currently accumulated value at that point in the expression, and eventually it's going to get us the right answer. It's going to go all the way up to 120. And then of course when it hits this base case here where n is equal to 1, it's going to hit the if statement. Then it's going to return the accumulator, which is 120, which is here. So as you can see here, we don't have to multiply anything to the front or the back of the recursive call at every step. And this actually allows us to optimize the amount of space that is needed to completely finish this computation by a ton. We don't have to ever store anything that we haven't done yet other than the recursive call at every given step. So this is what we call a tail recursive function. A tail recursive function is a function whose recursive call is the last step in any given part of the function. So in our case, because we have the recursive call factr in the else statement, notice how there's nothing else other than factr being called. So that's why you can see here that there's none of those cascading patterns that we saw in the previous fact function. We no longer have to have this issue where n is being multiplied over and over and over again without actually being able to multiply to the next value because it hasn't finished all the recursive calls yet. So that actually saves us a lot of space. Now you might be thinking, this is not a very big deal, right? It's just multiplying a lot of numbers. The computer is going to be able to handle this anyways. Why do we care? Well, so you might be right. This might not seem like a big deal for this factorial function, but for other functions, for example, like the Fibonacci sequence, this is actually going to come into play quite a big deal. And this is because not only can it optimize for the amount of memory that a computer has to continue to allocate, it can actually save you a lot of time as well because it doesn't have to recompute values that it has already computed. I don't have time to go into that too much in this video, but if you're interested, feel free to check out this video that I linked in the description below. It goes into more detail on why this sort of tail recursion approach saves you a lot of time in that kind of stuff as well. Okay, so to finish off this video, there's one more thing I want to add. So you might be thinking, hey David, what if I don't want to have this one sticking out at the very end of this function call that we want to address here? And that's a very valid concern. And this is a very common way that functional languages, or just languages in general, will handle this type of issue. Let's say we just want to do factr5 and get the answer. But here we're not going to be able to get the right answer because right now the OCaml top level is giving us a function. And that's because we haven't put the 1 into the second input yet. Here's how we can get around that. So what we have here, I'll briefly explain, is a nested function called helper within a function called factr. So as you'll notice here, if you look carefully, this function here, these 3 lines, the helper function, is the exact same as the factr function that we described up here, with the exception being the name, of course. Okay, so it's the exact same. What's important, however, is that we're reusing this helper function to call it on this input n and this accumulator 1. So if we do this, you'll indeed see that it's a function that takes in an int and gives us an int. So if we do something factr of 5, then we'll see we actually get the same thing that we wanted, which is 120. The way this works is that because we know the base case of the factorial function is 1 all the time, we can sort of lock in this base case scenario into the helper function. And this is actually a very common approach using accumulators to program loop-like constructs in functional programming. It's a very common and useful technique, so I just wanted to leave you guys with that. All right, that's all I want to say for this video. If you have any questions, feel free to put it into comments below. If you liked this video, thought it was a little bit informative, helpful in any way, please leave a like and subscribe. All right, see you guys next time.